and welcome to the 2016 online Basic Skywarn class. And for those of you that have never been through a Skywarn class, a little bit about Skywarn and what it is. Skywarn, every season we train volunteers, citizens throughout the country, not just in the South Central Texas area, on how to observe storms and how to report back severe weather to the National Weather Service. And why is that important? We have a lot of equipment and technology available to us, including radar, that can see information within the storm, but there's limitations to this technology. In particular, the radar can't see the lowest few hundred to the lowest 1,000 feet off the ground, depending on how far you are away from the radar. So it can't really tell us what's going on at ground level. So we rely on spotters kind of as our nation's first line of defense of telling us what's going on as far as severe weather on the ground. They can give communities downstream time to prepare. So we can take the information we receive from spotters and verify, or in some cases tell us what we're not seeing on radar, and use that in our warning information that we give out to communities and citizens. So our Skywarn spotters that are going through this training right now throughout the country are trained to identify severe storms and how to report back to the National Weather Service. A little bit about the National Weather Service. Our main mission is the protection of life and property, but it's a community effort. We rely heavily on emergency management officials, law enforcement officials, heavily on the media to help get the word out, help get our warnings and watches out to the public. And people like you, Skywarn spotters that are trained to observe severe weather safely and report back to the National Weather Service. So who is the National Weather Service? The National Weather Service is made up of around 122 field offices and several national centers. We have the Storm Prediction Center, which looks at severe thunderstorm and tornado watches throughout the country, and they are located in Norman, Oklahoma. We have the National Hurricane Center, which does the official tropical cyclone forecasts, and they are in Miami, Florida. We have a Climate Prediction Center that does more long-range forecasting out of the D.C. area. Many of our computer models are run out of the D.C. area. And then we have this patchwork of 122 field offices, local field offices that monitor the weather in that area and issue the actual watches and warnings for that area. A little bit more about the area that my office serves. So we are the Austin-San Antonio office. The physical location of our office is in New Braunfels, Texas. We are responsible for about 33 counties in South Central Texas, including the I-35 corridor from San Antonio to Austin. Westward to the Rio Grande, Eagle Pass and Del Rio, Texas are in our area, and then east and southward into South and Southeast Texas. Some terminology before we get started. Many of you may have seen maps like this on the Weather Channel or local media with lots of different colors and terms that are used. The terms advisories and watches and warnings are kind of thrown out there, and it can get confusing sometimes. So we're just going to break down quickly what these mean, in particular what the watches and warnings mean. But first, the weather advisories. Those are issued by the local field offices for weather conditions that aren't necessarily life-threatening, aren't conditions which someone will have to take protective action, but more for the nuisance type weather conditions. So say a dense fog advisory may result in slower speeds that you have to travel on the roadway, or a flood advisory may just mean some ponding of water on the roadway, but it's safe to kind of still travel through. Watches, on the other hand, are issued for the events, the weather events that are life-threatening or are threatening to property. So the conditions where you'll need to take some type of action to protect your life or property. Watches are issued ahead of these events. So when conditions are favorable for tornadoes that day, the Storm Prediction Center may issue a large geographical region under the threat for tornadoes, and they'll call that a tornado watch. If conditions, say, are favorable for flash flooding that day, our local office may issue, say, a flash flood watch. Doesn't necessarily mean that the conditions are ongoing yet, just that ingredients are there for those conditions to occur that day. Warnings are issued when either we have ground truth from our spotters or other means that the conditions are occurring, or they are about to occur. The conditions are imminent. And so geographically, the warnings are much smaller in size than the watches. We kind of fine-tune and pinpoint the actual geographical areas that are at risk from, say, a tornado, or say a hailstorm, or a flash flood. And so those are called warnings, and those are when people need to seek the shelter now. Those are when the conditions are occurring or imminent. So what do we kind of consider severe? What do we actually issue the watches and warnings for? As far as hail goes, we define severe hail as 1 inch in diameter or greater. That's the size of a quarter or greater. That's about the threshold where some minor damage can start to occur to some vehicles, and so that's why we use that as the threshold for severe thunderstorm warnings. Tornadoes, defined as a violently rotating column of air that's connected from the ground all the way to the cloud base. Obviously, tornadoes are life-threatening. That's why we issue tornado warnings and tornado watches for them. Damaging winds. So it doesn't take a tornado with a violently rotating wind going up into a thunderstorm. Winds that collapse down out of a thunderstorm can cause just as much damage, and we call those types of winds straight line winds. Sometimes they're referred to as microbursts, but the general term is straight line wind. That's associated with the winds that come down out of a storm. The threshold that we use for severe straight line winds is roughly about 58 miles per hour or greater. That's about when you'll start to see some damage to larger tree branches, perhaps some power lines being damaged, poorly built structures, maybe mobile homes, some roofs, roofing material may come off, and so that's the threshold we use for damaging straight line winds. And then flash flooding. As little as 6 inches or more of flowing water can sweep a person off their feet, and 2 feet or more of flowing water will float most vehicles, almost all vehicles, including the larger trucks and SUVs. And so we issue flash flood warnings for those cases. We recommend that people have multiple ways to receive our watches and warnings. Certainly television and commercial radio are one way. Smartphones now are enabled to receive government warnings. Sometimes you have to go into your settings on the smartphone and turn on the government warning capability. But assuming you have that capability turned on your smartphone, if you fall within one of those boxes that is within a tornado warning or a flash flooding warning, your smartphone will go off when you're in that warning. Before we get into kind of the meat of the course on how storms form, how they become severe, and clues you can look for, we're going to talk about some hazards associated with storms and some safety information. We always want our spotters to be safe. We don't teach our spotters to go out and chase storms. We teach them how to observe severe weather safely from a safe distance. So let's start first with lightning. And some of these facts you may remember from grade school or middle school about how hot lightning is, hotter than the surface of the sun. On average, every year in our country, we see about 30 deaths per year attributed directly to lightning. Hundreds more are injured every year. And you can see in the picture kind of why lightning can be dangerous. In the bottom right picture, you see this lightning bolt traveling out away from the parent storm, the actual storm. We have seen cases of lightning traveling out as much as 10 miles away from where it's actually raining. And we call those bolts from the blue for obvious reasons. If lightning can travel that far away, there can be clear blue sky above you and you can be struck by lightning. So the general rule that we like to give people is if you are close enough to hear thunder, even a distant rumble of thunder, you're close enough to be struck by lightning. As far as the lightning fatalities by month, This chart here is a national average. Kind of the lightning capital of the world is Florida, and most of their storms occur during the summer months, and they usually every year lead the country in fatalities from lightning. This is the reason that that chart is kind of skewed towards June, July, and August being the peak months for lightning fatalities. For Texas, in May is actually the month where we see the most deaths from lightning. Let's talk about flash flooding. In particular, this is our #1 storm-related killer here in South Central Texas. We call this area of South Central Texas the I-35 corridor, and the hill country and the rise in elevation that goes up into the hill country, the Balcones Escarpment, as Flash Flood Alley. And so there's a number of reasons we see dangerous flash floods in this area and flash flood fatalities in this area. One of the reasons is just the nature of the topography and the hills in this area combined with the soil type can lead to very quick runoff of heavy rainfall. The second reason is this rise in elevation that occurs leading up into the hill country along the edge of the Balcones Escarpment near and just west of the Interstate 35 corridor can sometimes lead to an enhancement of thunderstorms. It can lead to thunderstorms becoming stationary over a region, or what we call training over a region, and dumping incredible amounts of rainfall in a short amount of time. And the third reason is just the urbanization that's taken place and the increase in population. So if we have this risk for flash flooding in this area and we're putting more and more people into this area, certainly see the dangers from that and the increase in fatalities that we have seen over the last couple of decades from flash flooding. This next map here represents the flash flood fatalities by county in our county warning area over the last 25 years. And in our 33 county warning area, we've seen 143 deaths just from flash flooding. And you can see them lining up in what we call the Flash Flood Alley. These deaths represent half of the state total, half the total for Texas. So essentially half of all the flash flooding fatalities for Texas occurs across the hill country and the Interstate 35 corridor from San Antonio to Austin. So I mentioned earlier that as little as a foot of water can displace 1,500 pounds, and 2 feet of water can displace most vehicles, and that's not flowing water. Once you start to add flowing water into the equation and horizontal forces on a vehicle, you can quickly see that almost all vehicles will be floated with as little as 2 feet of water or more flowing over a roadway. And so big vehicles and trucks and SUVs are at risk from flash flooding, from drivers making the mistake of thinking they are safer and trying to cross through low water crossings. If you're from this area, you may remember this past May of 2015 was a particularly wet month across the whole state, but in particular this region of Texas. And the weekend of Memorial Day was an exceptionally wet period. In particular, there was a big flash flood that occurred on the Blanco River in south central Texas on the evening of the 23rd leading into the 24th of May. And so this radar loop here shows you where all that rainfall occurred the afternoon prior to when that flash flood occurred. And so you can see these storms kind of sitting stationary west of San Marcos, east of Boerne, Texas, dumping incredible amounts of rainfall the afternoon of May 23rd. This next loop here shows you what we call the velocity of the radar. It's showing us how fast the winds are within inside the storm. And so these greens next to these reds are circulations that are occurring. You can see this circulation that kind of sits stationary southwest of Blanco and northeast of Boerne, Texas. And this incredible amount of rainfall here across these locations in these two counties produced their own circulation within inside the storm. And so here was the rainfall that occurred that afternoon and evening of the 23rd. Highlighted here in the yellow circle, you can see a bullseye of 6 to 10 inches with some isolated pockets of over 12 inches. Over a foot of rain fell that afternoon and evening. If You notice also on the map, we have Wimberley and San Marcos, Texas, noted on the map east of this circle. Those two cities only saw about 2.5 to 3 inches in Wimberley and about 1.5 to 2 inches in San Marcos that afternoon. There wasn't actually much flash flooding occurring that evening in Wimberley or San Marcos, so many residents went to sleep that night not understanding the magnitude of the rainfall that had occurred upstream that was headed their way that night. So all that rainfall that occurred back near Blanco fed down into the Blanco River watershed through Wimberley, San Marcos overnight, resulting in a large flash flood. This video here was taken from a home along the Blanco River in Wimberley, Texas. This resident is filming the water rushing in from upstairs into their downstairs area. You may look at this video and think that must be storm surge or something from a hurricane or a tsunami, but no, that was a flash flood along the Blanco River that caused that rapid rise in water. And just how rapid was it? Well, here is the river gauge that sat on the Blanco River at Wimberley. On a normal day, the gauge reads about 5 or 6 feet as far as the river height goes. That evening, as the flood wave made it down to Wimberley, the river rose 30 feet in just 2 hours, eventually washed the river gauge out, or later able to go in and estimate a crest of around 44 to 45 feet. So essentially the river rose almost 40 feet in 2 to 3 hours that night. And so you can see the dangers and why we call these flash floods. Some of the pictures here along River Road in Wimberley. You can see homes swept off their foundations. That water all went downstream. This is the next morning after it had stopped raining. So all that rain upstream had occurred the afternoon of the 23rd. This is the morning of the 24th in San Marcos. And you can say the Blanco River at I-35 inundating Interstate 35 and shutting it down briefly the morning of the 24th. So you can see the dangers and hazards with flash flooding, in particular this region of Texas. Let's talk more about some other hazards, hail in particular. We haven't seen many fatalities in our country from hail. If you've ever seen a green or bluish green tint to a storm, sometimes that can be an indication that there's large hail contained within the storm. So just a visual clue to kind of look out for within storms. So I mentioned earlier that we define severe hail as quarter-sized or greater, 1-inch hail or greater. We will actually take any hail report we can get as a spotter. If you come across maybe pea-sized hail or penny-sized hail, that's important information for us to know too. That can help us calibrate what we're seeing. If you're able to take pictures and get them to us, that's great. Just remember to use some frame of reference. Place a coin next to the hailstone or a ruler next to the hailstone to help us get a better gauge of how big the hail is. So this map here represents all the storms last year that produced severe hail, 1-inch hail or greater. Just over 5,400 storms that produced large hail. That may sound like a lot of storms. You can see a lot of them are lined up in the central part of the country. But that's actually kind of an average of what we normally see every year. I mentioned towards the very beginning of the presentation that it doesn't take a tornado to produce a lot of wind damage. Winds that collapse down out of a storm, what we call straight line winds, in some cases microbursts is what we call them, can produce damage that looks like tornadic damage. So all these blue dots on this map represent storms that produced straight line winds, the winds that collapsed down out of a thunderstorm. And so we had 12,500 of those storms last year that produced severe straight line winds. And again, that may sound like a large number, but that is actually about average. Kind of a time lapse of what an actual microburst looks like, what those winds coming down out of a storm look like. And so here in this first picture you see the rain and the rain-cooled air collapsing down out of the cloud, the initial stage of the microburst. It hits the ground in the impact stage, and it's kind of at this stage that the threat is there for damage to property beneath the microburst, and obviously a threat to aviation. We've seen aviation accidents in our country's history attributed to microbursts. Eventually that rain-cooled air spreads out away from the impact area, the impact zone of the microburst, horizontally along the ground, and what we call a rain foot. The leading edge of that boundary of that rain-cooled air and that wind we call sometimes a gust front or an outflow boundary. I've marked that here in yellow. And it's along these edges of these boundaries, these outflow boundaries, these gust fronts, where we can also see wind damage. And so again, straight line winds collapsing down out of a storm can cause wind damage, just like tornadoes with wind going up into a storm. Here's a video taken from a dash cam last year in New Orleans. This dash cam is going to turn here and look upwards. You'll see a train going across an elevated train track, and you can see a gust of wind blow these large train cars off the train track down to the ground. These winds were estimated at about 100 miles an hour, and they were determined to be straight line winds. Again, winds collapsing down out of a storm. So just goes to show you the power of microbursts and straight line winds coming down out of a storm. So what about tornadoes and the violently rotating columns of air with wind going up into a storm? All these red dots represent tornadoes in our country last year, in 2015. Just over 1,200 tornadic reports. Remember a couple slides ago, the microbursts and the straight line winds were 12,500. So we see 10 times as many straight line wind events in this country as we do tornadoes. But tornadoes are very hazardous. They are life-threatening. A little more in definitions here as far as a funnel cloud versus a tornado. I mentioned earlier a tornado is defined as a violently rotating column of air that's connected from the cloud base all the way down to the ground. A funnel cloud is not connected all the way down to the ground quite yet. There is a rotating column of air that's connected to the cloud base. It's hanging out of the cloud base, as you see in these pictures, but there's no connection all the way down to the ground quite yet. We classify tornadoes on a scale called the Fujita scale, ranging from EF0 to EF5, with zeros and ones being the weakest tornadoes. These are the tornadoes that have wind speeds up to 110 miles per hour. We are fortunate that in this area of Texas, the South Central Texas area, these account for most of our tornadoes in our climatology. 81% of all of our tornadoes are these weak tornadoes. So they don't cause much in the way of deaths. They are dangerous. They can cause significant damage and destruction of mobile homes and other poorly built structures. But well-built homes, as long as you're in interior rooms and lower floors away from windows and outer walls, you're generally okay in these types of tornadoes. These account for only 7% of all of our deaths in South Central Texas attributed to tornadoes. Because they're so small and not on the ground for that long of a period of time, they can be difficult for us to see on our radar, and many times we won't get confirmation from spotters that they're occurring. So most of them actually go unreported. The EF2s and EF3s, these have wind speeds of 111 to 165 miles per hour. These account for much less of our tornadoes in our climatology here in South Central Texas, only 18%, but they cause 42% of all of our fatalities from tornadoes. So obviously when you're getting up to these types of wind speeds, these are going to start causing considerable damage to even well-built homes. And they are much wider tornadoes and on the ground for much longer periods of time. So these are usually pretty identifiable on radar. We don't usually miss these on our radar. And obviously, if we have spotters on them, we get good confirmation on the ground from what's going on. The violent tornadoes, the EF4s and the EF5, wind speeds over 165 miles per hour, in some cases over 200. Very fortunate that these account for less than 1% of all of our south central Texas tornadoes, but when they have happened, they account for just over half of all the fatalities in this area from tornadoes. Just a little fact here, the last EF5 tornado that's actually occurred in the state of Texas, the whole state, was the Gerald tornado that occurred back in 1997. So let's kind of get into the meat of the course here. How ordinary storms form, how they become severe eventually, and some visual clues for you to look for from a safe distance. So first, how do ordinary storms form? Not severe storms, but just ordinary storms. We typically need three ingredients. We need moisture, not just down at the surface, but through a pretty good layer of the atmosphere. We need some type of lifting mechanism, like a cold front, or some type of disturbance in the atmosphere to help move the moisture vertically up into the atmosphere. And then we need a term called instability. And instability essentially just defines once we get the air moving upwards into the atmosphere, we want to keep it going upwards. And so the more unstable the atmosphere is, the faster and the more likely the air is to continue to rise vertically into the atmosphere. On the flip side, the more stable the atmosphere is, the less likely it is for air to rise. So when we have those three ingredients, we get the recipe for storms to develop. For ordinary storms, not severe, there's a life cycle to them that you can see. It begins with what we call the towering cumulus stage, where all the air motion is upward into the cloud. The air is condensed into cloud droplets that you see as a cloud. There's no rain or hail falling yet out of the cloud. Everything's going up. We call that region of the cloud the updraft of the storm, the updraft of the storm, the air that's rising vertically into the atmosphere. Eventually, as the raindrops become heavy enough to fall back down, they fall back down in what we refer to the downdraft of the storm. The updraft brings the fuel for the storm up into the cloud. The downdraft brings the rain and the hail and that rain-cooled air and those straight-line winds down out of the thunderstorm. And so during the mature stage of an ordinary thunderstorm, the updraft and the downdraft coexist for a very brief time. During that mature stage, you can often see a flat top to the cloud, what we refer to as the anvil of the cloud. And it is essentially a layer in the atmosphere way up high, sometimes 30, 40,000 feet up in the atmosphere, where it is stable and the updraft can no longer rise, so it flattens out, and we call that portion of the cloud the anvil of the cloud. Finally, the dissipating stage. Eventually that rain-cooled air hits the ground and it spreads out away from the downdraft, and it eventually chokes off the updraft, that fuel for the thunderstorm. And so the whole thunderstorm dies. And you can note in the dissipating stage, the clouds begin to look a little bit more wispy in nature. As opposed to that previous slide, they looked a little bit more cauliflower in appearance, and then you had the anvil on top of that. During the dissipating stage, the cloud structure looks a lot more wispy and feather-like. That whole life cycle from beginning to end of an ordinary storm can take as little as 30 to 60 minutes. So what do we need to take that ordinary storm and turn it severe? There's a fourth ingredient we look for in the atmosphere called wind shear. Well, what is wind shear? Wind shear we define as an increase with wind speed as you go up in the atmosphere, and or a change in direction of the wind as you go up into the atmosphere. So why is that important? Why is wind shear important? Essentially, wind shear will take the updraft and tilt the updraft downwind. That's important because as the downdraft develops, it will fall out and hit the ground away from the updraft. So the two will coexist for a lot longer period of time. The updraft and the downdraft will coexist for a lot longer period of time, allowing the storm to grow. In some cases, if the low-level wind shear is strong enough, you can get tornadoes to form beneath the updraft of a storm. So some visual clues as a spotter to look for. The first two things we like to tell spotters to look for from a safe distance is, number one, where can you see the rain or the large hail falling? That is the downdraft of the storm. Second, where do you see a rain-free base next to the downdraft? That is the updraft of the storm. That is where the air is rising up into the storm. That rain-free base is the zone of where the air is rising up into the storm, and where you see it raining or the hail falling is the downdraft, the air coming down out of the storm. So if you can spot those two things, you can start to get some clues on what to look for next. By the way, the larger hail, the heavier stuff usually falls out first. It's heavier, so it will usually fall out closer to the updraft, and the smaller raindrops usually get deposited further downwind away from the updraft. So, some visual clues that you can look for as a spotter. Crisp edges, a cauliflower-looking appearance to the cloud. We're not just talking about a normal towering cumulus cloud, a normal puffy cumulus cloud. We're talking about a cloud that has grown to 40, 50, sometimes cases as high as 60,000 feet up in the atmosphere. Those crisp edges, those cauliflower appearance to the cloud structure can be visual clues that the storm is strong to possibly growing severe. Again, the anvil is the top to the thunderstorm. If you see an anvil in the storm and you're way out many miles, and on top of the anvil you see a top that develops, we call that an overshooting top. And so when you see an overshooting top, that represents an updraft that has grown so strong that it has continued through the stable layer and punched through it and continued to rise. And so an overshooting top can be a visual clue to look for as a spotter, as an indication of a strong or severe thunderstorm. You'll need to be out many, many miles away to see an overshooting top. You can't be directly beneath the storm. 10, 20, sometimes as cases as far as 50 or 60 miles away, if you're in open country, you can see these overshooting tops. So, back in closer to the storm. If you found your downdraft where it's raining and your updraft, the rain-free base to the storm, and you note a lowering over time to the rain-free base and a gradual rotation to the rain-free base. That is something to pay attention for as a spotter. We call that a wall cloud. A lowering of the rain-free base and a gradual rotation to the rain-free base is called a wall cloud. It won't be a violently rotating cloud yet, just a slow lowering and gradual broad rotation to it. You'll need to watch it for many minutes. You won't see this happen in a few seconds. This will happen over the course of many minutes. Why is a wall cloud important? Why do we need to know about that? Wall clouds can be precursors to tornadoes. Tornadoes like to form beneath wall clouds. Not all wall clouds produce tornadoes, but some do. So if you ever observe a wall cloud, that would be something to report back to us. Another type of cloud called the shelf cloud. At first glance it may look like a wall cloud, but wall clouds are smaller in size, maybe a few hundred yards across. Shelf clouds can go many miles in length. We call them a shelf cloud for obvious reasons. They look like a shelf. Shelf clouds are associated with the downdraft of a storm. The wall cloud, the previous cloud I showed you, is associated with the updraft of the storm in the tornado region of a storm. Shelf cloud are the winds and the rain-cooled air that are coming down out of the storm. And essentially this cloud forms along that leading edge of that rain-cooled air. Another visual clue to distinguish the difference between a shelf cloud and a wall cloud. Shelf clouds in most cases point away from where it is raining. So if you find out where it's raining, and in this picture I've highlighted where it's raining, and you note this cloud pointing out away from where it's raining, that is an indication of a shelf cloud. Again, associated with the downdraft of the storm, the wind that has traveled out away from the downdraft of a storm. So again, shelf clouds point away from where it's raining. Downdraft straight line winds are what would be noted with those. Wall clouds, in some cases, can point back towards the rain, and they are associated with the updraft region of the storm and potentially where tornadoes can form. Some other clues to look for. If you find the rain-free base and you note a new line of clouds going up, flanking away from where it's raining, we call that a flanking line away from where it's raining. Those can be an indication that a storm is growing in strength, possibly becoming strong or severe. So as you increase the instability in the atmosphere and you have the wind shear in the atmosphere, you increase the threat for severe weather. The two most common types of severe weather that we get here are squall lines and supercells. So let's talk about both of those next. Let's first start with squall lines. On radar, to us, squall lines are very organized systems of storms, lines of storms that go many miles, sometimes several hundreds of miles in length. They are often associated with straight line wind damage. They can produce large hail, and on occasion brief tornado spin-ups along the leading edges of these squall lines or out ahead of them, where we get individual cells that develop out ahead of these squall lines. Again, these are usually isolated tornadic outbreaks and usually weaker tornadoes. The damage that you can see after straight line winds, after these squall lines, at first glance may look like damage that a tornado must have produced. So in these images here, this large tree uprooted, this light plane flipped over, this power pole completely snapped, and this roof taken off this barn, you may think that a tornado must have produced that wind damage, but no, this was straight line winds from a squall line that produced this wind damage. Supercells, on the other hand, are very discrete, isolated individual storms. They don't go for hundreds of miles like a squall line. They are individual isolated storms. They form on days where we have moderate to strong amounts of wind shear and instability in the atmosphere. And so they are of significant threat to life and property. These are the types of storms that produce the very large hail, sometimes baseball or softball sized hail, and usually the long-lived tornadoes and sometimes the stronger tornadoes. From a spotter's perspective, all those visual clues we have talked about, you can often see in a supercell. So you can see here in this picture where it's raining, you can see the rain-free base here and the wall cloud that's formed beneath the rain-free base and the tornado beneath the wall cloud. You note traveling up into the storm beneath the rain-free base, you'll note the updraft is tilted with height, indicating wind shear in the atmosphere, tilted in this picture from left to right as you go up. You'll note the overshooting top on top of the anvil, another indication I gave you earlier of a storm that is possibly strong to severe. The flanking line of new clouds going up along and out away from the rain-free base in the rain, another indication of a storm that's possibly growing in size and strength. So all those visual clues you can often see in a supercell. From a radar perspective, what do they look like to us on radar? Unlike a squall line that's a line of storms, these look like hooks or commas on radar. We call these hook echoes on radar. Essentially, the region we are looking for tornadoes in these hooks are at the points, the apexes of these commas or these hooks. That represents the updraft region of the storm and the potential of where a tornado could be. Where the larger hail would be located, will be falling out first and located usually in the brighter reds and pinks on radar. And then the larger raindrops and medium-sized raindrops are deposited further downwind from there. So that's what a supercell looks like on radar to us. So not all supercells produce tornadoes. In fact, most actually don't. But when they do, they tend to be the stronger, more violent tornadoes. Sometimes our supercells, as I mentioned, can produce the large hail, and in some cases they can produce intense microbursts. In this image here on the right, that is one of our Doppler radars out near Del Rio, out near Brackettville, Texas. The radar shouldn't look like that. That was caused by a microburst, those winds collapsing down out of a storm that caused the damage to the radar. And in this case, those winds were estimated at over 100 miles per hour. So some spotting techniques and some safety information for you. Obviously, we want our spotters to be safe. Again, we don't teach our spotters to get in vehicles and chase storms. You want to observe severe storms from a safe distance. Sometimes in the initial stages of when a tornado is developing, the middle portions of the tornado can be invisible. You'll see a funnel hanging out of the cloud base, and you'll see debris being kicked up on the ground, so you know there's a connection all the way to the ground, so we can call that a tornado. But in some cases, the middle portion will not have filled in yet. This can be dangerous if you happen to have large trees or hills or buildings obscuring the debris on the ground. You may think it's just a funnel cloud and not a tornado. Sometimes storms that are strongly rotating and producing a lot of rainfall, the rain can become wrapped all the way around the updraft. We call those HP supercells, high precipitation supercells, and they're dangerous because they can obscure large tornadoes within them. There's clouds that can be mistaken for being dangerous or tornadoes. The one on the right we call a tail cloud. Sometimes the moist air from the downdraft can be ingested back towards the updraft in what we call a tail cloud. The one on the left is very ragged in appearance and detached from the cloud base. We call those scud clouds. Those are usually very harmless clouds. They'll usually be traveling pretty quickly horizontally, usually not exhibiting a rising motion and not rotating, but detached and ragged in appearance. And again, harmless clouds. We call those scud clouds. Some tornado lookalikes. This cloud on the right here, sometimes in the dissipating stage of a thunderstorm, as the downdraft kind of shrinks in size, it may look like a tornado from a far distance, but just pay attention to it, and if you see things falling down towards the ground, again, an indication of the downdraft of the storm. Picture here on the left was actually taken from San Antonio. It's a picture of steam rising off the power plant in Calaveras Lake. These can be mistaken for tornadoes in industrial areas where steam or smoke rising off of stacks into cloud bases can look like tornadoes. And people not familiar with the area and not knowing that an industrial area was located down in that area can mistake those for tornadoes. So what do we need to know about? Obviously tornadoes, the rotating, violently rotating columns of air that's connected from the cloud base to the ground. Funnel clouds we need to know about. Scud clouds, the ones that are detached from the cloud base, not rotating, we don't need to know about. Some spotting techniques and safety information again. Safe distances. Low-level clues to look for. You need to be close in, but at a safe distance, 1 to 4 miles. 1 mile might be pushing it. More like 2 to 4 miles is a safe distance to be at. Flash flooding, for obvious reasons that we saw earlier in the presentation. Flash flooding is our #1 storm-related weather killer. So do not drive through flooded roadways to observe severe storms or get away from severe storms. You can be swept away. As little, again, as 2 feet of water will sweep most vehicles off of roadways. Safe places to be from high winds and tornadoes. Interior rooms, lower floors, away from windows, away from exterior walls, preferably interior closets, interior bathrooms are safe places to be. The worst places to be as far as high winds go, mobile homes, poorly built homes offer little protection, and even the lower wind speeds, the lower 60 to 80 mile per hour wind speeds can cause damage to poorly built structures. Vehicles can actually offer protection for lightning. If you're caught outdoors from lightning, in lightning and can't get to a structure, a vehicle can offer protection. Now, as far as high winds and tornadoes, they can obviously be picked up and tossed around, and you don't want to be in a vehicle as far as a shelter goes in a tornado. We've seen more and more cases over the past decade or two of people riding out storms underneath highway overpasses. This is becoming dangerous. Obviously, you got people stopping the interstates. That's dangerous. Reporting severe weather back to us. I'll have this 800 number on the very last slide if you don't have time to write it down. But this 800 number you can use as a spotter to report severe weather back to us. Tornadoes, rotating wall clouds, the precursors to tornadoes, and funnel clouds are all things we want to know about. Any type of wind damage you come across is important. Hail of any size, so not just the quarter-sized hail or greater, but even the smaller pea-sized, marble-sized, penny-sized hail is important clues for us to know about. Usually we get good reports from our TxDOT officials, our county officials on flooded roadways, but if you happen to have rainfall equipment on your property that's sited well, when it is safe to do so after the storm has passed, you go out and check your rain gauge and you note an extreme rainfall amount has occurred, you can report that back to us. And by extreme, what do I mean? Usually 2 inches more per hour will start to cause some issues in this area. For completely saturated, it can be a little bit less, but 2 inches more per hour or greater can be kind of an extreme rainfall rate that we start to look for as far as flash flooding in this area. If you can't call us or don't want to call us, you can also report severe weather back to us online through our website at weather.gov/Austin or weather.gov/San Antonio. Go to that website, find the Submit Storm Report tab, click on that tab. That will take you to a form to fill out. Once you've reviewed the information and submitted it, what's neat about this is it comes to our office. It just does not go to an email inbox that we don't get to for a while. It actually alerts on our workstation to get pictures to us. The best way right now to get pictures to us is through social media, in particular Twitter. If you're on Twitter, if you're familiar with hashtags on Twitter, if you use the hashtag EWX Spotter, we monitor that hashtag. So if you tweet a picture of some type of wind damage or tornado or hail, use the hashtag EWX Spotter. You can also submit them on Facebook to us. If you're not on social media, if you call the 800 number and you have a pretty good picture to get to us, just ask for a good email address of somebody that's working, and you can send that picture to them via email. So last few slides here, we also have a mobile website, mobile.weather.gov. It acts very similar to an app, so mobile.weather.gov is a great site to go to. There's a free app also available called mPING that was developed in partnership with NOAA, the National Severe Storms Laboratory, and OU. Another way for people to get storm reports, crowdsourcing weather reports. You can submit not only severe storm reports and rainfall information, you can also submit winter precip via this app. And so they're very good about sharing this information back to the National Weather Service. This does get into our computer system. So if you submit an mPING report, we will get that in our computer system. Final bit of information here. If you do have a good rain gauge that can measure rain down to the 100th of an inch, and it is sited well on your property, away from trees, away from the roof line of your house, there's a program called CocoRAS run by Colorado State University that is free to sign up for. You can sign up for a free account, and every day you can submit online or through their free app your daily rainfall reports in the morning of what you've received the past 24 hours. They're very great about sharing that information back to the National Weather Service, and we will get rainfall reports. What's neat about this is you don't have to check it every day. If you go out of town for the week on vacation or something, when you get back, You can submit via their app or online via their website a multi-day precipitation report. And so that can give us better detail on where the heavier rainfall pockets have occurred. It can help us kind of quality control what the radar is estimating as far as rainfall goes. In some cases, it can really give us some great information. This case here, back in 2008, a storm sat stationary just north of New Braunfels for a few hours over one location, over one CoCoRaHS gauge, and produced just over 7 inches of rainfall in a few hours. Whereas some other CoCoRaHS gauges out away from it, just a few miles, received barely anything. So CoCoRaHS.org, a free program to sign up for and report rainfall information back to us. So we thank you for attending this online Basic Skywarn class. We hope it's been informative. Have a great rest of your day and week, and stay safe this severe weather season. Thank you.